So first, thank you very much for coming. First, I'll start by introducing myself. I was originally trained as an electrical engineer. I later got a PhD in computer science at the University of Rochester. I was professor at University of Virginia for 6 years, and then went to Texas Instruments in corporate research laboratories. In 2009, I moved to ARM as Director of Graphics Research, and I've been chairman of the OpenGL ES working group since 2006. The OpenGL APIs form a family with different members that are suited to different markets. On the desktop, we have desktop OpenGL, which is the leading API for cross-platform. So it is the standard 3D rendering API for Linux. It is the standard 3D rendering API for Mac OS. It is available on Windows, at least through Windows 7. So if you want to target all desktop platforms today, it is the most portable 3D API that we have. OpenGL ES is the mobile subset. That's the API created by the committee which I work on. It is found today on all mobile APIs, or most mobile platforms, including smartphones, where we have a lot of portable software, but also embedded platforms. Automotive, it's found in many, many digital televisions today. More and more, we see digital TV using the same API that's used for smartphones. Finally, there's the new API, WebGL, which is just beginning to emerge into the market. It brings the API of OpenGL ES 2.0 into JavaScript and makes it available through HTML5. It's very new, and I'm not going to talk about it today. I will talk about OpenGL, particularly the newest features of the newest version of the API. And I'll talk about OpenGL ES, mostly about practical problems in writing portable code for OpenGL ES platforms. So we start with OpenGL on the desktop. This is a special year for OpenGL. The API is 20 years old in 2012. Since the first version in 1992, this is a very long time in the technology universe. So the API has obviously changed a great deal since that first version was released. This pace of change was slow for many years, but starting in 2008, it became very rapid. The issue was that for some years, Microsoft's APIs kept improving and OpenGL did not. And so progress was slow. In 2008, it became clear that this was a problem. And the working group decided they needed to catch up. So they began working very hard, released a new version every 6 months until this past year with OpenGL 4.2 in order to capture all the features of the Microsoft APIs. So with OpenGL 4.2, this process is now complete. With 4.2, we have the same feature set in OpenGL that you have in DirectX 11. Sorry, specifically in Direct 3D 11. There are still some features of DirectX which are not part of the 3D graphics. So what this means is that today, even the most advanced desktop content, such as the Heaven benchmark from Unigine, have an OpenGL mode, which you can select, and they will run if you have an OpenGL 4.2 driver. So I'll talk now about the newest features of OpenGL 4.2. The biggest change, the biggest step in OpenGL 4.2, and the biggest trend in OpenGL for future is the addition of computing features for the GPU inside the graphics pipeline. In OpenGL 4.2, we get two features. One is the ability to read and write texture memory and buffer memory from inside a fragment shader or a vertex shader. By the way, I am assuming that you know basically how the OpenGL model works, that we have a shader that processes vertex data, feeding a shader that processes fragment data. If that's a new concept for you, please talk to me after. I'd be happy to explain. In any case, in old versions of OpenGL, inside those shaders, you could not touch external memory. You could only consume attributes fed from the pipeline and sample textures supplied as texture uniforms. But with the new API now, you can directly read and write buffer objects. Of course, GPUs are heavily multi-threaded, so that creates a problem if you're reading and writing the same data from two different threads. You will have race conditions and concurrent programming errors. So to address that issue, we add atomic counters. These are external memory operations which can be read by an operation which reads the counter and increments it atomically, so that if multiple shaders do atomic increments on the same variable at the same time, they will all get consistent results, and no updates will be lost. So one question you might ask is, why do we have computing in OpenGL? Why do we need it? The Khronos APIs also include OpenCL, which is in many ways more powerful and more flexible. So what is this for? The OpenGL computing facilities are not meant to replace OpenCL. If you want to do, for example, a big physics simulation and then view the results as graphics, it's best to use OpenCL for the physics simulation because it is very flexible and powerful. And it has good facilities for producing a buffer of data and giving it to GL, sharing it with GL so that GL can render it. But these operations are kind of heavyweight, so you need a big computing buffer to give to GL. You can't pass very small amounts of data very quickly. For that kind of computing, you want to use the new computing features of OpenGL. It's for when you want to do computing very tightly coupled, perhaps at the level of a single fragment or a single vertex. I'll give an example in the next few slides of how you can use this to do some interesting rendering, which is not possible in OpenCL, or which is difficult. But first, I'll explain some of the other new features. The first one is immutable texture objects. The idea with immutable texture objects, in old OpenGL, you can create a texture and you will specify the pixel type and the texture size, and then later you can change it anytime you want to. This is a problem for the driver because, of course, the GPU and the CPU are both touching the texture all the time. And so there needs to be synchronization. You have to, if you want to change the texture, you have to stop the GPU, which is not good for performance. So with immutable texture objects, we now have the ability for the application to say, this texture's size is fixed, the pixel type is fixed, I may change it, but the GPU never has to stop. So this helps performance. Instance transform feedback allows you to make an instance drawing call where you draw multiple copies of an object with, for example, different positions. A whole herd of animals, a whole group of soldiers can be drawn with one drawing call. And the transform feedback, the new feature, is that you can capture those into a buffer which the CPU can inspect or which can be used for multipass rendering. So this also helps performance. BPTC is the 8-bit per pixel texture compression standard from Microsoft DX11. As part of becoming equal with DX11, we've added this into OpenGL. And finally, shading language packing allows a shader program to take multiple low-precision numbers and pack them into 32-bit words so that they can be stored to textures or to buffer memory or used in transform feedback to give those numbers to the CPU. So this saves memory bandwidth, usually. So now I'd like to go back to this GPU computing question and give a simple example of what this is useful for. So we'll go to a classic old problem in computer graphics. I want to draw transparent objects, multiple transparent objects that overlap each other. So the traditional way to do this, you would use alpha blending because you have a transparency for every surface that you render. But in order to get correct results, you must render the objects first the most distant, then the next, then the next. Otherwise, the result will be incorrect. So for example, If I draw red, green, blue, I get one result. You can see the blue is in front. If I draw the same objects in a different order, blue, green, red, we get a different result. So the order must be correct, otherwise the result will not be correct. But this is a problem. The application doesn't want to know the order. It's hard work to sort the objects so that things are drawn in correct order when everything may be moving, the camera may be moving. If you have to sort on the CPU by distance, that's expensive. Also, if some of these objects can cross each other, then no order may be correct. You really need to sort for every pixel, not for every triangle. So we have this leads to the problem of order-independent transparency. How can the application draw transparent surfaces in any order without worrying about distance and still get correct results? So there are some papers that you can read, classic ways to do this. One of the most popular is depth peeling, but the trouble is that this approach, I don't want to explain it, take too much time, but this approach requires a full screen drawing pass for every layer. So that can be quite expensive. K-buffer also has this issue. We'll start with I'll explain a very simple way to do this. There are better ways, but it's an easy to explain example. So what we will do is when we render transparent objects, we will not worry about the depth. They can be drawn in any order. But every time we render, instead of putting the pixels into the frame buffer for display, we will just collect a list in a series of texture layers of all of the fragments with their color and their depth. And so we'll draw everything. Then when everything is done, we'll draw one more full screen triangle. And there we'll collect, for each pixel, we'll collect the list, sort it in the GPU as part of the shader program, and composite the pixels from back to front to get the correct result.
Question.
Yes?
Who do the sort? The GPU do the sort, or the software do the sort?
The GPU will do the sort as part of the fragment shader.
Does current GPU support it? The latest GPU hardware supports this type of software.
With OpenGL 4.2, you have the ability to do this. Actually, as you'll see, we're going to keep the list in a texture array. Texture arrays came to GL, I believe, in 4.1. So it's possible, if you know the dimension of the array, to just do a bubble sort or some very simple kind of sorting algorithm in the fragment shader to get the correct order. I'll show a picture.
So is the shader doing the sort?
The shader will do the sort.
No.
It's not special hardware, no. Yes, it's the shader. So the example I'm using, by the way, comes from a simple web block, but there are other methods. I have another paper which you can read, which is better, which I'll give in a minute. So I've explained the basic idea. We want to collect a list of transparent fragments. But now let's see how we'll do this exactly. First, we'll keep one array, which is the size of the frame buffer, which is integers, which stores for every pixel the number of transparent fragments that have been drawn to that pixel. Initially, nothing's been drawn, so all the counts are 0. Then we have a layer texture, which has 2 values per pixel. One is a color, and the other is the depth of the color for the transparent fragment. Suppose the application draws a small triangle that covers this pixel. The fragment shader for that pixel will atomically increment the count. So when it does this, the fragment shader receives 0, but the number changes to 1 instantly. So the fragment shader knows that it can store its color and depth in layer 0 because it returns 0 from the count. The number changes to 1, and the color and depth are stored here. Now, sometime later, another triangle is drawn, and it also draws to this same pixel, and it does the same thing. It atomically increments the count, so it receives 1, so it knows it can write its value into layer 1, and the value changes to 2 at the same time. So you can see as we draw more and more layers, they will build up until we have them all. So at the end, we have these layers. We know that there are n valid depths and colors at this pixel, maybe some other number at other pixels. But the order of depth is random because the application doesn't care, it just writes. So now we have to do one more step, which is we'll render a full screen triangle that covers every pixel. And in that fragment shader, we read the count. For this pixel, it says you have n fragments to sort. We read the layers, we sort them and composite them back to front in software, in the shader, in the fragment shader, and store the result to the frame buffer. And that's how it works. So this is a simple example. There are some issues, and there are some ways we can make it better. I won't talk in detail about it, but to give you an idea. The most obvious problem is that if I have many, many transparent layers, I need a lot of textures. Each texture is as big as the screen. So if it's a mobile device, I'm going to have a problem with memory. Too many layers. But we also know, if you look at a large number of transparent layers stacked together, some of them are very important, but some are not. The ones that are at the bottom don't affect the color very much. Mostly the ones in front affect the color, or the ones with a very large alpha. So if one of the fragments has a small alpha and it's far down in the stack, we don't care very much, so we can approximate it. So there's a very nice, to do this well takes some work, and I don't have time to explain, but there's a very nice paper in High Performance Graphics 2011 called Adaptive Transparency. You can find a PDF file on the web if you Google for it. That explains very well a nice way to do this. I think it's the best work right now, but maybe next year you guys will do the best work and we'll have new papers. So that's my example of how GPU computing can be helpful to solve interesting problems in graphics. And I hope it's clear why this would be hard to do in OpenCL. Because here we're making use of the rasterization hardware and the texture hardware very tightly interleaved with the computing process. And this method works well for that. It would be hard to do in OpenCL. Are there any questions about this or about OpenGL 4.2 in general? Yes?
Yeah, I just want to get the impression when you see this adaptive transparency, you mean you could basically limit to the number of layers to a practical number?
Yes, to a practical number.
And how much is that usually?
In the paper, they give 3 examples. One is a case where they were able to do it with 8 layers, which is pretty good. In one case, they used 24, which is a lot. That would concern me some. But it's always a trade-off of quality versus memory requirement. The basic method that they use is they build the list, and when the list is full, they ask the question, which layer is the least important to the result? And then they combine that with some other. They find the 2 least important layers and they combine them. So it's a good idea. Okay, so I'm going to switch now to talk about OpenGL ES, keeping an eye on my time. OpenGL ES, we do not have a new version. We have had OpenGL ES in the market actively since I guess devices began to ship in 2009, so it has been some time. In that time, OpenGL ES has become hugely successful, the most successful API Khronos has ever issued. It's the standard rendering API for Android, for iPhone, and for mobile versions of Linux underneath, such as Tizen, for example, which is a JavaScript application layer, but OpenGL ES underneath, WebGL, and others. There is a mobile Linux called Linaro, for example, all using OpenGL ES. On these platforms, it is used not just for games, but it's also used for the user interface, for the window system composition, for 2D rendering as well as 3D rendering. And in many cases, if you have OpenVG or browser or anything, it's put together using OpenGL ES. So there's no new API this year, but what is new for us and very exciting is the progress of OpenGL ES in the marketplace. 2011 is the first year that we began to see big commercial products such as Unreal Engine 3 or the Unity game engine ported to OpenGL ES2, which allows game developers who are familiar with these tools to easily create 3D games that run on top of an OpenGL ES2 platform. I hope at some point you'll have a chance to see my colleague Robert. Where is Robert? There he is. Yes, thank you. My colleague Robert from ARM is one of our FAs here in Shanghai. He has brought some devices. One of them has a demo which has the Unity engine running some content created for that, which is interesting to see. But what is exciting for me is that this gives us high-end content. For example, this is the Unreal Engine. The game is called Infinity Blade for iPhone. This is a demo done by id Software of a version of their Rage engine, id Tech 5 engine for Rage, but it's a very small version because id Tech is huge. But what's exciting is that now we're starting to see applications developers delivering content that has very high value. People pay high prices for this, so there's good business in this. And this is what we have wanted for 10 years. We started this business so that there would be an ecosystem in which hardware vendors, platform owners, software vendors, applications developers would all produce content that consumers would want and that consumers would enjoy. And that, until that chain is complete, we have not succeeded. But it seems that this year, that chain is complete now. As I say, we have very high-end content appearing on mobile devices. Very exciting for me. So what my working group is doing today, we have two major projects underway. The first one is to develop the new version after OpenGL ES 2.0. We have been working hard on this since about 2009. We have always said we wanted to be careful because if we released it too soon, then it would create a problem for OpenGL ES 2.0 content. People would be unhappy with it. Developers, software developers, would not be sure if they should use it. So we didn't want to disturb the market. It seems now that the market is healthy. As I said, we have lots of good content now. So maybe the market is about ready for a new API. I cannot talk about future because Khronos has an agreement that we don't discuss future until it's publicly released. But I will say that we are working hard on this and it will not be very long, not a long time, before the next version is ready. As part of this project, we are working very hard. This ARB is the name of the desktop OpenGL working group. And so a major part of our work now is to take my committee for OpenGL ES and the desktop committee, the ARB, for desktop OpenGL, and work more closely, try to make the APIs more similar so that you have good portability of applications between desktop platforms and mobile platforms. Yes, John?
I have a question. What's that an image out there on the screen?
This.
Yes.
Thank you, John. This is a 4-page reference card, which is available from the Khronos website for free download, which contains the entire OpenGL ES API very concisely expressed, including the shading language. So if you're programming on OpenGL ES, but not every day, and you have some trouble remembering how do I use this function, what are the arguments for that function, that reference card is a handy thing to have. You can just print it out. We didn't bring any copies, did we? Sorry, sometimes we have copies, but it's very expensive to bring them from the US. But anyway, if you go to the Khronos website, khronos.org, and look at the OpenGL ES registry, I believe is where you can find the specification and also the manual pages and the reference card. As I said, the ARD and the OpenGL ES committee are trying to work more closely together to make the APIs more similar. And this is beginning to work because some of the features in OpenGL 4.2, such as the immutable textures that I mentioned, were actually developed for the next mobile API, and we co-developed them. We agreed with the desktop group that we would go the same way, so the code would be more portable.